you have to build solutions. So, and I do not have access to machines. I do not have access to lab equipment, but yes, I have to continue my job, right? So it presented unique challenges to us, and that's what I want to share. Like for me, learning experience, like there were certain things which could be handled easily from home. There were certain things which required lab accesses. So as my work basically involved engineering IoT-based sensing and communication systems, so this absence of a lab meant adopting drastic measures. And these measures basically ensured that I could continue my work from home. And this approach, I was meant to build industry grade systems, but whatever systems I could build, I purchased systems of Amazon, which were like low cost, commercially available solutions, sensors and Arduino boards and those kind of things. So in this presentation, basically, I'll be sharing like what was required for me to set up this bare basics IoT-based condition monitoring system at home, locating equipments around me on which I could test. I definitely did not have access to industrial equipments. So I was stuck in my apartment home in Kolkata. I did not have access to any lab facilities. So whatever I could lay my hands on at home, I made use of it. So it's more of my work from home experiences, and it's basically the lessons learned during my at-home stay and system development for scientific monitoring. So this is the basic background of my talk. And before I go into the system, I hope so it's going to be more of a computer science thingy. So people, non-domain people might get a bit bored, but bear with me. So the main motivation, the objective I needed to fulfill was monitoring of industrial machinery. So these machineries, they tend to be three-phase systems, electrical systems. So for example, you see in this picture, you have a three-phase wiring diagram. You need to attach various sensors to it. The sensors go to a monitoring system. This is a typical standalone system. So, but I have to monitor, like maybe in a building or a home, a smart home environment, we have motors, power sockets, lights, fans. So how do we determine the various operational states of these devices and appliances? Like the first solution that might come to your mind is maybe attach a relay to it and you can basically control the on-off states of these devices. But no, I do not want to attach a relay. Wiring will stay as it is. I do not want to tamper with it. I just need to have an add-on solution which will enable me to monitor these systems, and especially the states these systems are in. For example, even if you attach a relay, it will only tell you whether the device is on or off, but it is not going to tell you, like for example, this first figure, this motor, right? It's not going to tell you whether the motor is running a load or is it simply rotating in air. So those kind of states I'm talking about. Going to tell you whether the fan is running at full speed or whether is it running at suboptimal speeds. So what are the states these devices are going through? So in a nutshell, this was my task I was assigned to do for industrial monitoring systems. And when you start breaking down these things into smaller components, so most of the industrial machineries, industrial systems, be it lathe machines, CNC machines, robotic arms, they have motors, right? Most of these consume electricity, right? So can we build a solution? Can we find an alternative approach by working from home in which I can mimic these systems? I can build a solution which will work on these mimic systems, and later on, can I just port these mimic systems onto the real systems? So a basic IoT solution will have these 5 components. this is the basic solution. There will be various nitty-gritties, fine-tuning. You can put in security, you can put in various optimization approaches, lots of things, right? So I'm just talking about the broad outline. You have sensors, you have a server. At one point, you have some kind of database. You might need maybe an on-site visualization, or maybe you want to present your visualization to a remote user. And it's good to have some kind of analytics attached to it, so that you simply don't see like the loads and loads of data coming to you and you are not meant to interpret that data. So some kind of analytics always helps, which helps you decode the data. So what goes behind designing such a system? So suppose at the first stage, you have various sensors which do the sensing part. Then you bring in some kind of, let's say, a gateway or an edge device. So let's say a Raspberry Pi, right? So you will have two kinds of communication interfaces. One is the inbound interface, which communicates with the sensing or the sensors. You have an outbound interface, which sends your data over the internet. You have some kind of server in it. You have a database in it. And then again, you can include multiple stuff in it, like analytics, visualization, everything, right? And Raspberry Pi is a pretty robust device. So this is, let's say, the edge layer, the cloud layer, or the remote side. So if you see, like, most of the things are same, it's repeated. I've knowingly put up different things like visualization and analytics on the cloud side, but these can be easily ported to the gateway thing. So this is what I'm trying to build when I'm saying that I want to build an end-to-end monitoring, IoT-based monitoring system. So what do I need to get started at home? So I chose to have basic, commonly available hardware. Like you can buy this off Amazon or common sites as RoboKits and these kind of things, right? So you have Arduino boards, you see a Raspberry Pi over here, a simple breadboard, simple registers, connecting wires, a multimeter. That's it. That's all the hardware you basically need to get started at home, even for building these complicated solutions. And let's say if you ignore the Raspberry Pi, instead of a Raspberry Pi, maybe you tried collecting the data on your laptop or your computer. So if you ignore the Raspberry Pi, I don't think the cost of the whole thing or the hardware components are going to cross 1,000 rupees. It's going to be lesser than 1,000 rupees. So, building such a complicated solution at home within 1,000 rupees, it's pretty good. Jumping to the software parts, first one is like if you recognize the logos, first one is you need an Arduino programming IDE. You need Python, like this is what I used. Then most of you must have heard about Docker. So these are, how should I say, these are not exactly virtualization tools, more of a containerized approach to building solutions. So you have kind of isolated solutions on a system. For example, I have Docker containers for InfluxDB, which is a time series database, MySQL Docker container, which is a relational database. This symbol like a sun, this is Grafana. It's a visualization dashboard tool. Mosquito is basically an MQTT server. And then you can have a cloud account. I used Microsoft Azure. If you don't have a cloud, maybe you just simply put your data onto a remote PC. That works pretty well. And this Apache is the HTTP server. So this is what I used. And one thing to keep in mind is, except for the cloud, which is you can pretty much ignore, none of these softwares will cost you anything. These are free, these are open source, and it's always good to use them. So once I had my pick of hardware and software, started with building a simple current sensing device. So first one is a clamp-on current transformer. You just hook this onto a wire carrying current. Then a basic circuit using simple resistors and capacitors, which acts as the filter circuit. It gets connected to an Arduino board, and you can have interfaces such as a Bluetooth module or something like that. Even like if you are using Node MCU boards, these are much smaller, much cheaper, and interestingly, they have an onboard Wi-Fi module. So I prefer the Node MCU modules. So I chose to use the UDP part. So this was the current sensor I configured. Similarly, I built a vibration sensor. So this whole thing, this whole combination, I'm calling it as a sensor. You just attach it to some device and you expect data over the wireless interface coming onto your Raspberry Pi. The data storage and visualization part on the Raspberry Pi, it had the same interface. If I was using Bluetooth, data was through Bluetooth. If I was using wireless Wi-Fi connection, the data was through UDP. And I wrote some drivers in Python, which basically collects data from this UDP port 9000. This is the port I chose, and pushes the appropriate data to the appropriate database. Then I had to write another Python driver, mainly 20-30 lines of code. That's it. Very simple and straightforward. You extract data from the InfluxDB database and push it to the cloud, where there is a visualization tool, the Grafana, and this is attached to a website. And so you basically have a website on which you can globally access your data from the current and the vibration sensors. So one more thing to note here is this is the bare basics minimum setup required for an end-to-end IoT solution. However, sometimes it was seen that there are data drops, especially when the data sampling frequency is quite high. Like, for example, the vibration sensor, it tends to have a high data push rate, and most of the packets get dropped. So there was consistency. To make things more manageable, it is advised that some kind of an event-triggered server is used. So to make the whole system more robust, I simply used an MQTT server. So the driver now pushes data to the MQTT server, and whenever a new data arrives, it starts writing to the database. And the rest of the stuff are pretty much the same. Now, let's say that these are the basic systems you have up and running. You have created an end-to-end system where you sense parameters from various devices or instruments. You process it basically, you store it in a database, you have records, you transfer it to the cloud, you visualize it, and anyone globally can basically get access to that data visually. So now the question is, what do I measure at home? Since I'm locked up at home, like, what do I measure? So if you look around, you will find plenty of things to measure. For example, these were the things I used. So a bulb, a table fan, even a blender, a steam iron, and the last one you see there is a kitchen fume extractor or a kitchen hob. So most of these devices, all of these devices run on electricity. Most of these devices have motors. So the motorized ones are going to be pretty, shaky, like they will produce vibration. So I attach my vibration sensors to these devices, and all of these devices have a current sensor attached to them. I'll show you in the forthcoming slides. So these were the things I use or misuse. For example, this one. So I attached a small vibration sensor to the kitchen fume extractor, and I attached a power sensor. If you look in the figure on the right, I attached a power sensor to a wiring leading to a bulb. So the whole thing was set up wirelessly in my house. If you see, there's a breadboard behind the tablet. There are lots of wires coming out. It looks very untidy. And the live data is coming to the dashboard through the Raspberry Pi. So whatever the configuration I showed in the previous slides, you had databases, you had visualization tools, you had some kind of analytics. All of this is being run on the Raspberry Pi, and I can directly access data from the Raspberry Pi, and on a browser tab in this tablet, I can basically see my dashboard. So this is how it looks. If you start from the bottom left side, so this is one of the initial versions, like maybe 1 month into development, when I had all the components. So I had a Arduino module, a Bluetooth, a sensor attached to the Arduino board. It senses data. If you see in the second figure, see it's sensing something over the serial port. This data is now transmitted over Bluetooth, Raspberry Pi, and finally, if you look at window 4, you see this is a very basic. This was my primitive dashboards Grafana interface. You can actually visualize whatever data is coming in it. After modifying, this is after the second month. Like you see, I took up a blender, attached a power sensor to it, attached vibration sensors. I managed to, clean up the circuit. I soldered it. There's the data coming over MQTT in the black windows. And in the far right, you see over the browser, I can actually see the states the device is going through. So suppose it is off, it's drawing lesser current, like when the motor is not running. When the motor is running, the current draw increases, and you see a rise in the power consumption in the graph on the right. So this was the primitive state. Now I tried making things more interesting. If you see here on the topmost part, yep. So on the topmost part, this portion, this shows the RMS current which the blender is using. This shows the power draw. So most of these things, the topmost plots, they deal with current and power. At the bottom, I included a small bit of analytics, which I'll cover in the later part of this presentation. So it basically tells you when the device is switched on or when the device is switched off, even if it is drawing some kind of load or not. So interestingly, this model I tried using on a blender, I tried using on a table fan. At the back end, I put up a clustering model with some primary data sets, which I obtained from these instruments themselves. And the system could basically tell that, yes, your device is switched on, your device is switched off. If you see this portion, so this is the only state when it says, yes, the device is active. Rest of the portions, it's not active. And whenever the devices were active, I was only sending those time intervals to the cloud. Also helped me save a lot of data and bandwidth. So this is what it looked in the later stages. Lots of things. It had current, it had temperature, it had humidity parameters, it had vibration parameters, displacement parameters, and things started getting complicated, right? And mind you, I'm using those same set of basic sensors which I showed earlier, and some of these things were derived parameters. Then, for the sake of having a clear-cut reorganization of what can be accessed where, I decided that the high volume of data, such as the current, the power, the vibration sensor data, accelerometer, and the displacement readings, I'll keep it stored on the Raspberry Pi itself. I'm not going to transmit it to the cloud, just to save some data. And for the slowly changing data, such as temperature, humidity, I basically transmitted those few values to the cloud. And on both the dashboards, like the local dashboard, which you see over here, this is the local one. And on the remote dashboard, which you see over here, I could actually like simultaneously get data, and I could stream my progress over the globe. So this is what in the final days my experimental setup looked like. So if you see that I managed to solder most of the things, very less loose wires, connections got improved. So I had a IMU sensor which had accelerometer, gyroscope, and inbuilt temperature sensor. I attached it to detect the vibrations on the blender. I attached a current sensor to detect the current consumption in the blender and the apparent power the blender was consuming. And I had a DHT sensor at the very right side, if you see, that measures the room humidity and temperature. And all of these two nodes, node 1 and node 2, these are node MCUs, and they have inbuilt Wi-Fi's in them, and they wirelessly transmit data to a Raspberry Pi. So I had a very high polling interval of 10 to 20 milliseconds, which considering the components I'm using, considering those components, it's pretty good. Considering industrial equipment, like proper industrial equipment, it's not that much. For built from home solutions, it's pretty good. They wirelessly connect to the nodes wirelessly connect to Raspberry Pi, and I had a UDP based connection for faster data transmission. I faced a problem like in terms of the vibration data, I was not getting good results. So I actually had to open up my blender. You see here, this is how the current sensor attachment looks like on the blender. And in terms of vibration sensor from the outside shell, I actually had to open up the blender and place the vibration sensor on the motor inside the shell. So yeah, so there was this air gap which was preventing the vibration sensor from getting accurate results. Once I placed it on the actual motor, the results drastically improved. And now I was ready to do some kind of analytics onto the data that was incoming into the system. This might look pretty straightforward, but one point to note here is I was building this system considering that I had to deploy this same exact system maybe whenever I was allowed to join my new working place, ensure that this same system would work on industrial machines. Right? The same system is going to work on industrial motorized equipment. Maybe the power, the current, those kind of ranges will change. The sensing range is going to change, but the data flow, the communication, everything should remain same. In fact, the analytics too. So this is now what I included. So if you recall from the previous outline, I had MQTT, I had drivers which stored data to the database. I parallelly included an analytics module in it. So it's still storing in the database as well as the live data is used for analytics. That is determining what states the device is going through. Interesting demo. This is the mixer I was using. So I basically put up the attachment and filled it half with water, and I started calling it like half load state. So if you see on the plots here, the topmost part, the extreme right one shows the current draw when there was no load attached to it, when I was running the mixer, and it was basically rotating in the air. When I attached this yellow attachment with half load, that is half filled it with water, it was drawing a bit of more power than no load condition. When I filled it up completely with water, you see the full load condition, the power draw is, current draw is significantly more. So this basically gives you an idea that these devices go through different states. So consider like you have a milling machine. Milling machine is, let's say, analogous to your hand drills you have at home or you must have seen with carpenters. So you have milling machines. So the mill rotates, the spindle rotates. So it's rotating in the air. It's going to draw a different kind of power. As soon as it touches a substrate, maybe wood or metal, it starts drawing more power, right? Because it needs more effort to rotate the motor. So if you can determine those states just from these power signatures, maybe you can say that, yes, my machine is doing this at this moment, just on the basis of power or maybe vibration signatures. So that was the whole aim of what I had to do. So based on the data I captured or I managed to capture, this is what I was getting. This is what you see here is from the vibration sensors. These are the raw data I was getting. The off state, the bottommost part, if you look at this one, these blue lines are the vibration produced when the device is off. These are, let's say this is the noise. These are the vibration produced, and it's certainly higher in amplitude when the device is on and it's rotating in the air. And when you put up a substrate or attach a load to it, the device starts vibrating significantly more. If you analyze the spread of the data, if you check the FFT of the data. So basically, when you have raw data, I access this data from the database I used. So once you have these kind of data, you can do any kind of thing. Like you can do signal analysis, you can do a Fourier analysis, you can even, let's say, train machine learning models. So that is just what I did. So I trained a basic clustering algorithm, and I made the machine identify whether the device is in the off state, which is this one, right? Or the device is in the on state and it's rotating in the air, as in no device, like no load is attached to it, which is this state. And the final one you see here, this is when the device had some kind of load attached to it and it was rotating. I put up this trained model in the Raspberry Pi, and this is actually what you're seeing here is from the live data I was running that model through. And whenever new data was coming in, the system started predicting, like, yes, my device is running some kind of load, or it is not running any kind of load. So if you revisit this graph, if you see here, this live status thing, so even if there is power draw over here, this is not recognizing this power draw. Wait, this is supposed to be moving. Okay, anyway, so you see here corresponding to this. So this was the on state, right? And corresponding to this, the clustering algorithm detected, like, yes, this was my on state. And in the live status, it started showing on. There was a cumulative on time thing, like it started recording for how long the device has been kept on and so on. So now I had a basic setup which would enable me to visualize data remotely from various appliances. I had a system which could monitor the current consumption, monitor the vibration signatures, and it had a basic analytics module which could determine what states the machine was going through. So interestingly, since I built all of these things on a Docker container, so I just shared the Docker container file to my colleague in UK, and within a day, the whole system was up and running, because he just had to put up that Docker file in the Raspberry Pi, and all things started working on their own. And now the whole system is implemented on these big platforms. I started working on homemade blenders and fans and irons. Now this whole thing, just the data thresholds have changed. Is this whole system, this whole setup is now being used for monitoring industry grade milling machines, lathes, and robotic arms. So this is one of the work setups. So the sensors won't be visible here, but yeah, you get the idea. And like this is what the final solution looks like. So this is exactly what we have covered. It's a bit more detailed, like what portions have been included, like where I'm fetching the data from, and so on. So moral of the story is what were the lessons learned during this process, right? So some of the lessons learned where there is a fight between cost and accuracy. So lesser is the cost, the accuracy is bound to suffer. Of sensors, uh, lower cost devices like processors and those things is not going to significantly affect your solution, but the sensing is going to be significantly affected. The range of measurements is going to be limited. Like within 1,000 rupees solution, using 1,000 rupees solution, you cannot expect the, you know, uh, multi-lakh solution which is used in an industry. So at most you will be able to mimic some of the features and some of the functionalities, but you cannot expect it to be like simply a competitor to a solution which is lakhs in cost. So there will be some kind of trade-off there. If you're working on electronics, working from home, your solutions might not be good enough. They might be noisy. You need to have lots of patience to determine like why is the noise being caused, some loose wires, broken wires, loose connections, and so on. And the most important thing is always use version controls and maybe go for portability solutions such as Dockers. So whatever solution you build on one site, you just share a Docker file with your friends or your colleagues, and they can easily recreate it and verify what you have done is right or not. Yep. So that's all from my side. So let's discuss.
Hello. Am I audible, sir?
Yep.
Uh, Sir, in your opinion, what are the prerequisites for developing such a system? And just a follow-up question to that, what led you to look at a mixer and then open it up and then put up sensors there? Thank you.
So regarding the mixer thing, I found at my home which used some kind of motor and which was not that costly. So like the other options were too costly. I could not basically open up my home washing machine. And so mixer was the only like lesser riskier thing which I could lay my hands on. And regarding prerequisites, since at the beginning, at the onset of this presentation, I've said like these are my experiences, domain of things I'm working on. This might not hold true for everyone. Like people working with chemicals, people working in agriculture, maybe you need to look into some different kind of solution. But for people like me who like, I could either work on simple theoretical stuff. So a pen and paper would be sufficient for me. But since my work involved working with systems, so I had to find some way of so that I could spend my time productively. So maybe that was one of the motivations.
Thank you, sir.
I think that's about it.
Hello. Hello, Anand sir. I have a question.
Yeah.
What were the major challenges in the setting up the environment that you have done in the experimental setup? Sir, my question is, what were the major challenges that you have faced during the setting up of your experimental environment, which can be considered if someone want to simulate for further experimentation?
The most challenging issue I faced was lack of measurement tools. For example, like especially if you're building an like electronic solution which is going to further measure something, right? In an instrumentation solution, you need measuring capacity to determine like, yeah, this is the accuracy I'm getting, or my system is working fine or not. So on that part, I was pretty much blind because I did not have access to I did not have access to signal generators or those kind of things at home. So mostly I worked using a small cheap multimeter, and for people who are starting newly into this domain, things might look a bit complicated, and debugging it quite an issue. So
Okay, sir. Thank you.
Yeah, that's my.
Okay, sir.
Thank you all. Thanks for coming.